Morning, everybody. Sorry about the delay.
Morning, Professor.
There's a lot going on here this morning. It's pretty noisy with the construction. Okay, before I forget to tell you, tomorrow, I normally hold the Friday study group time. And tomorrow, I'm just double checking my calendar here. I have to delay it an hour. So I will be available from noon to 2. So 12 to 2 p.m. tomorrow. I've got a few things going on. I'm doing some lab work down at Stanford using their electron microprobe. And what it is you take, well, I can show you, I've got them here. So a box of thin sections. These are glass slides. Maybe you can see. They have a very thin slice of rock on them. And we can put these in an electron microprobe. And what it does is it uses an electron beam to excite the electrons in the outermost valence shells in the different minerals that are in the rock, and gives off characteristic X-rays, X-ray energies. And you use those energies to identify minerals and also their elemental composition. So you find out exactly how much iron is in your garnet, or exactly how much calcium is in your plagioclase, that kind of thing. And we use it to use those data to establish the pressure and temperature conditions for metamorphic rocks. Actually, I'm working on some migmatites. And if you remember from the metamorphic chapter, I hope you do, that migmatite means a mixed rock. It's the rock got hot enough in granulite facies metamorphism. So the rock got pretty hot. It wasn't super deep. These were regionally metamorphosed rocks, caught up in the collision that formed Pangea. But basically, I'm looking at what was going on during that mountain building event, that collision event. And that was 1 billion years ago. So trying to establish the pressure temperature conditions of the rocks, and also to figure out the melting history. So they're really funky rocks. They have these crazy melt structures. They don't look like any other metamorphic rocks I've ever worked on. So that's kind of fun. But we use the mineral composition data to put into numerical modeling program. It uses thermodynamic data for minerals. So like their entropy, the Gibbs free energy, just all of those chemical characteristics of the minerals to establish like which minerals are stable together at different pressures and temperatures. So I'm trying to reconstruct what was going on and like the tectonics of that collision. And it's kind of crazy because it's, 1 billion years old. But it's no different working on these rocks than any other rocks. Like I moved from working in the Himalaya and the Western Himalaya in India, looking at similar rocks. They were granite, they weren't migmatites, but they were high grade metamorphic rocks. And so relatively high pressures and temperatures, like 700 degrees Celsius. And we're talking maybe 15 kilobars. What is that? That's like 45 kilometers deep, which is middle crust for the Himalaya, because the Himalaya are like 70, 80 kilometers thick. Where was I going with this? Anyway, the processes in the Himalaya that are 50 million years old to looking at processes that are 1 billion years old is the same. It's the same. You still, you're still comparing the data that you get from one place to other places to try to figure out the history. And anyway, it's always fun to get new data. It's exciting because you're getting answers to questions that you've had. And Yeah, anyway, so doing that on Monday and Tuesday, but there's preparation work that has to be done ahead of time. The thin sections have to be coated with a very thin layer of carbon so that they're conductive. That way the electron beam, when it comes down and hits the rock, the energy, there isn't excessive energy at that point. That energy dissipates off the sides of the thin section, and then you just get the mineral chemistry from just the point underneath that electron beam. So it's you can get lots of data on a single crystal because the beam is only the width of an electron, so it's tiny. Anyway, that's what I am up to. The exam is open. I finally finished it late last night. Some of the questions, and before we get going on the lecture, I just want to make sure that you know, some of the questions may look familiar, similar to things that you've seen before, and that's intentional. Beware that they're not the same questions. I went through any that are similar. I went through and edited them for clarity and also to use language more like I use in class, so that, I clarified terms like fluvial. I made sure that you knew that meant rivers so that you don't have to memorize those terms. Remember, like I said, lacustrine, fluvial, alluvial, all those. If you're a geology major, that's a different story. But if you're just taking this class for general learning purposes or general education and your lab course, then you don't need to learn that. You just need to learn how it relates to the real world. Are there any, and just to clarify, I put a worksheet in lab 10 for Coastlines, the beach, a river of sand video. It's a 20-minute video, but I put this worksheet in the lab folder that has some questions for you to think about and to answer as you watch the film, just to keep your brain on track. I told you to take notes so that you were prepared to take the quiz that's about that video. And this worksheet is simply a note-taking sheet. You don't need to turn it in. All I want you to do to show that you watched and learned from that beach video is to take the quiz. Oh, okay. So there's a question about the test. How much multiple choice and written responses? Okay, so it is, again, a mixture of mostly multiple choice. I would say 3/4 of it is multiple choice, something like that. I didn't count. And there's some matching and just a tiny handful of true false questions. There are no short answer questions, although I did use some diagrams for the multiple choice questions. So instead of asking you to write about it, I'm asking you a question to interpret those diagrams within the context of a multiple choice question. So no short answer this time. You're welcome. Are there any other questions about the lab or the exam?
Professor, sorry, Mary. Will the exam's going to close on Sunday, correct?
No. Originally, it was supposed to be noon on Monday, but because I took too long getting it ready, I've extended that to 11:59 p.m. on Wednesday. So just before midnight on Wednesday.
Got it. Thank you.
You're
I have
welcome.
a question.
Yeah.
So is the Coastlines lab is that it, the video?
That's it.
Okay.
Because you have an exam this week, I wanted to keep it light.
Do we have to turn in our notes, or can we just? Nope. Okay, thank you.
Just the quiz. Your notes are for you to use to take the quiz. Okay. What else? So thanks for asking me about when it closed, because I did mean to mention that I extended that period. I didn't want to like drag it out forever because it's a holiday week and you should take some time off. I also didn't want you working on a lab over Thanksgiving break. I wanted you to have a break. So that's the goal there. We'll pick up again after Thanksgiving. I might record, I'm leaning towards yes, I will record a couple of videos for asynchronous watching between Thanksgiving week and the end of the semester, because we run out of time in lecture. But there are some things, like I'm worried you won't hear anything about deserts or glaciers. And there's some of you out there who probably want to know about deserts and glaciers. So those would be the two. That's right. I'm just thinking real quick. Those would be the two videos that would be asynchronous. Let's see, we've got chapter, so we're doing chapter 10 right now. That's the, or sorry, 11, that's Coastlines. 10, 12 is water. It's the mass movements and water that I want to make sure we cover together in class. So water is going to be surface water processes like rivers, mostly rivers, and groundwater. So a little bit about groundwater contamination. I think I have a pretty good lab for that to look at, like how you might figure out where a contaminated well is located. So you can kind of play environmental scientists for that lab. And mass movements are like landslides, rock falls, other things like that. Water would include things like flash floods. That's an important thing to do, because if you ever go, it's an important thing to cover, because if you ever go like camping out in Utah in the Canyonlands, you need to know about flash floods. And because they're so, excuse me, I gotta grab something. It's so common to have afternoon thunderstorms out in the desert that there are many occasions that you could be trapped. So you need to know where to put your tent or where not to put your tent. You need to know that if you're in a slot canyon, to get out and not to cross in your truck or your car, not to cross a flash flood, things like that. So that's what we're going to talk about there. What I'm going to talk about, we'll discuss. So, okay. Are there any questions about anything? I'd like to save specific questions about labs to the end of class, but otherwise, like, hit me with any questions you've got.
When does that quiz close for the lab 10?
They don't close. All of them have been open all semester long.
Oh, okay. I was just wanted to make sure.
Yeah. You ideally you do those the week of the lecture, so that, or after, maybe shortly after you hear the lectures. The idea is to quiz your knowledge from the textbook reading that I hope you're doing. If you find that you don't have time to do all of the reading, and I'm just trying to be realistic here, even though it's assigned and you're supposed to know that material, if you don't have time to do all of the reading, at the very least, scroll through the text, look at the figures, read the figure captions, check out the quiz questions. If there are things that you really don't understand, it's brand new, you should go read at least those sections to cover those. So don't ignore the textbook completely. That would be a bad idea. And then, so keeping up with the quizzes. I see in the grade book that some people have several quizzes, like all of the quizzes since the last exam still to do, or maybe most of them still to do. Make sure you do those before you take exam 2. And then like with the Coastlines quiz, that's not covered on exam 2. That's going to be exam 3 that you take during finals week. Just make sure that you get them done before you take that 3rd exam. But otherwise, all of those quizzes are open all semester long. So if you haven't done some, go back and do them and get the credit for them. At least partial credit, right? It can't hurt. It's better than a big old 0. All right, I'm gonna share my screen and let's get started. We just need to, and we didn't get very far on Tuesday, and I hope we can finish this today. I really, really want to finish this today. So where are we? We left off around here. Rip currents. Yeah, I was right there. Okay. Let me get my screen so I can see everything. Were there any questions about riptides? Okay, good. It's clear. Hopefully you will apply that knowledge when you go out to the beach next time. Okay, let us talk about where material comes from and how it spreads in the oceans, like clastic material. Clastic material is any like chunks of rock, whether they're sand size or clay size versus boulders. All of that material is clastic. That's material that comes from the continents. So all clastic material comes from the continents. And ultimately they're, gravity is taking them to sea level. So they're going to be expelled out into the ocean, and the finest material will spread out in a plume, kind of like what's shown here. So what this is showing here, you've got the swells are your waves. Remember the evenly spaced waves that are getting closer together, and the waves are getting higher as they get closer to the shore. The waves are also refracting, they're bending to be more parallel to the shoreline as they get closer. This stippled pattern in the river is like sand, clay, silt that's coming down the river and being expelled out onto the coastline. And it's showing the riptides that are pulling material out into the deeper ocean, or further out onto the that shallow ledge that's like the submerged edge of the continent that's there. And some of that material is going to make it to the deeper basins, the deeper parts of the ocean, if they get caught up in any underwater slides. We'll get to that later today. The finest material is going to be discharged out into plumes that are near shore. They stay near shore, but they're going to spread in the direction of longshore drift. So this diagram is correct. It's correctly showing the direction that the sediment plume would move with respect to longshore drift. How do I know? Because the angle, remember we were looking at the small angle that is formed between the coast and the incoming swells, the incoming waves. So that acute angle, that's the direction of longshore drift. It's moving in the opening of that small angle. It's moving out that direction. So this is moving off to the right in this case. The other thing that you're seeing in this is low discharge being like summertime or springtime, where there's water in the river, but it's flowing normally and there's nothing particularly special about it, versus following a storm or during a longer storm, the you're getting more material being discharged into the ocean. And so you have a larger sediment plume. You can see these sediment plumes on Google Earth or even Google Maps if you look with a satellite. Yeah, when you switch over from like street view to satellite view, you can see these things. I think we even saw one on an image of the San Francisco Bay. There's a turbid plume coming out from underneath the Golden Gate Bridge even. That's clastic material coming out. Okay, oh yeah, that's right. I said I was going to talk about the wave cut platforms and the terraces that form over time because we have this emergent coastline that's uplifting out of the ocean because of motion on our tectonic plate boundary. Because remember, we have oblique motion on the San Andreas. It's mostly right lateral strike slip faulting, but there's that small component of uplift. That's what we're seeing here. That's the uplift. Here, this is like a picture between somewhere between like Half Moon Bay and Santa Cruz, I think. I took the picture. I'm trying to remember. Yeah, it's that part of the coast where you see the sea cliff that is pretty steep, and you have the modern wave cut platform here where the current beach exists, and then old wave cut platform that 100,000 years ago was down here, but was uplifted over time along the tectonic plate boundary. We talked about waves being erosive, and that's real. I live in Pacifica. But I'm smart enough to know not to buy a house on one of these sea cliffs, because during storms, the waves come up high onto the beach. The waves are pounding the rock that forms the cliff. It undercuts the cliff, and then there's nothing left to support whatever is built on it. This happens to be an apartment building. It's not somebody's house. Yeah, look, outdoor deck now open. Yay, I'm gonna go sit on that. A lot of these buildings are gone now because they were too dangerous to inhabit. But like geology is happening all the time, I guess is my point. It's active. We have active processes. Okay, so this image shows one of these wave cut platforms, but without so much sand, so that you can see that there's rock down here. It's flattened because of the action of the waves over time. This isn't California, but I'm not actually, it might be Chile. Same idea with the cliffs though. This would have been an ancient wave cut platform just like this one. Okay, so this is further up in Mendocino, on the Mendocino coast. So that's Northern California, north of the Golden Gate. And what you've got here is there's the modern wave cut platform that's underwater here. And here's the older wave cut platform. And this is what you're seeing in this diagram. So you're seeing the eroded bedrock, like that picture I just showed you. You're seeing present day sea level down here with the current erosional platform. And then up here, you've got marine terrace deposits. So there could be fossils, there's lots of clastic material from the continent. So cobbles, sand, clay, silt size materials. It's not a sharp cliff at the backside of that ancient wave cut platform. It's formed a slope now, because what's happening is you're getting alluvial deposits. So the erosion that's happening from the even older wave cut platform and that slope is coming down and covering part of that older wave cut platform. So down here's the ancient one that might be 100,000 years old or thereabouts. And then the cliff would have been like in here somewhere, like back here. But there's all this clastic material that's been deposited to cover it. There's probably like a bit of the cliff right there. It's colored in so that you can see it's T1 is terrace 1. That would be the let's call it 100,000 year platform. And then it's showing here in orange where you would look over here to see terrace 2. So the even older terrace, look at it. It is hard to pick out. It's these bits here that are kind of flattened, and that aren't as there's a slope, but it's flat-ish. And behind it, again, another old sea cliff that is then covered with alluvium from above it. This pattern repeats down here too. This is Santa Cruz. So this is near UC Santa Cruz. This is Wilder Ranch. That is an open space area near UC Santa Cruz. And if you look in the right places in that part of the coast between Santa Cruz and Half Moon Bay, you can see as many as 4 or 5 terraces, old terraces. These are marked here. Terrace 1 is where these farmlands are. Terrace 2 is a little easier to see than that last picture, is right here, that flat area. Here's terrace 3 above it. Terrace 4 is even higher. So you're kind of seeing 1, 2, 3, 4 terraces that represent uplift over the last almost 500,000 years. So here's a plot showing the ages. So here's today at 0 years before present. This terrace here is dated at 120,000 years. Terrace 2 is about 200,000 years. Terrace 3 is measured at 320,000 years. Terrace 4 is about 400,000 years. So on average, it's around 110,000 years between terraces. But the other thing that this plot is showing you is that the uplift rate isn't exactly consistent, that there are slower periods and then there are faster periods of uplift. And this is just a nice view. And there's a nice view of an old wave cut platform and yet another one above it. How do we know that these are the ancient wave cut platforms? We find fossils. So there are fossils in the rocks and in the lithified marine sediments that are on those old wave cut platform surfaces. Questions about this? Okay, I guess that was the last slide for those. I did a mapping project like this as an undergraduate in a geomorphology class. That's landforms, essentially. Geo is earth, morph is shape, ology, study of. So wave cut platforms and the uplift of marine terraces is right up geomorphology's alley. That was a fun class at San Jose State. Okay. We've talked about the continental shelf. I showed you images explaining. Yeah, I did. I'm just checking my mind that I did. The edges of the continent extend out beyond where the edge, where our beaches are right now, where the coastline is. So if sea level were to drop again during a large glacial period, where remember the water is locked on land and so sea level drops, the beach would be out here somewhere, but eventually it gets to this slope, the continental slope, that is pretty steep and separates the edge of the continent from the oceanic crust, basically. So the rivers, especially large rivers, cut down through the continental shelf and form some submarine canyons, actually. So this is showing you like the steep incision there through the continental shelf. And then this would be a submarine canyon where deposits clastic material that comes off the continent. Um, of course, it's getting smaller and smaller as you get further out in the ocean, right? Because the smallest material is the stuff that makes its way farther out. And so we're getting some fine sands, clays, and silts that they're like underwater landslides. They're called turbidity currents. I've got some slides on that, that flow down these canyons and get deposited in the deeper ocean. So this is the continental rise, where it starts to rise out of the ocean basin, but the abyssal plain is essentially your deep ocean basin. And this is a cross section of what it looks like. So there's here's the beach, there's the coastal part of the continent. The continental shelf is shallow. Then you've got the continental slope. The rise is where the continent is actually, it's coming out from the deep ocean. And then the abyssal plains are down here. Oh, maybe I didn't show you the continental slope yet. I didn't. These are the slides that I wanted to show you. Okay, so you're probably wondering, what's she talking about? This is what I wanted to show you was, I guess we talked about what San Francisco Bay looked like and how the continental shelf extended out beyond, and the beach was extended out beyond the Farallon Islands. 120,000, no, it was not 120,000 years ago. It was like 40,000 years ago, I think, the last big glacial period. And so there were, instead of a bay that was submerged in seawater and river water, it was a system of rivers that still fed out through the Golden Gate and emptied into the ocean outside the Farallon Islands. This map shows the continental slopes in the very pale blue around the edges of the continents. So there's a pretty wide continental slope along the East Coast, and we hardly have anything out here. It's very narrow. That the reason that it's narrow here and wide here, we talked about, right? We talked about this being a passive margin. There are no active tectonics going on the East Coast. The plate boundary, so North American continent is here, but the plate boundaries are where? Out here in the mid-Atlantic, along that mid-Atlantic ridge. So that's what separates the North American plate from the European plate or the African plate. And then our plate boundary is here, right along the edge. And here, it's the San Andreas Fault, whether you're in Southern California or Northern California, it's the San Andreas Fault. From Mendocino north to British Columbia, it's a subduction zone, but that's not between the Pacific and North America. That's between Juan de Fuca plate and North America. Okay, so I wanted to show that. So places where you see a wide continental shelf are probably passive margins. Like here's an example. There's a subduction zone along the Aleutians. It's a sharp boundary. There's hardly anything behind that boundary up in here. There's no active tectonics, and so it's a shallow coast. To get in a little bit closer, remember we were talking about what does a beach in Florida look like compared to out here, where we've got these steep cliffs and you've got to like climb down steps cut into the cliff to get down to the beach in some places, or it's not everywhere, right? But out on the East Coast, it's pretty gradual. And that also means they're less protected on the East Coast from sea level fluctuations. So with a small sea level rise, let's say a meter, because they're predicting even more than that if we don't contain, the gases that are contributing to global warming. That meter of water is going to spread really far inland compared to a meter of water along the coast here that's going to hit a sea cliff and kind of stop. it would invade the bay and then flood the low-lying areas along the bay. But the coast is fairly safe. Okay. Let's see, so in the last 5 million years, this red line shows the high stand of sea level. So that's at one point where our coastline was. And then at its lowest level, about 20,000 years ago, during one of those glacial periods, the coastline was out here. So North America, the continent, was bigger. Oh yeah, and this line up here, don't forget this line. This is showing you the southern extent of the glacial ice, the continental glaciers that spread south, created the Finger Lakes in New York, and pushed a lot of sediments. There are a lot of drumlins. I don't know if anybody's from the Midwest or the East Coast, but there are a lot of glacial features in these areas from that history. Okay, so again, another picture. Here's a submergent coastline of Florida, where you're seeing like there's hardly, the land does not rise up above sea level very much at all. And the beaches are wide and flat. It kind of reflects that passive margin, that shallow, I'm forgetting the word, the coastline, wait a minute. If you guys aren't going to help me, I'll go look. Where's the word I need? Continental shelf. God. Okay. So the gradual continental shelf there, to give you the wide beaches. Here, coast, or the cliffs. So this is what it kind of, the difference would be. Like low sea level, this is what I was talking about. A low sea level, like today maybe, a 3 meter or a 3 foot or 1 meter rise might do this, have this sort of impact on an emergent coastline like us, versus how far inland it would spread if you had a low-lying coast. So there are some places that are more at risk to sea level rise than we are. Okay, another slide showing the continental shelf here. And then you can see the coloring represents its depths. So it's not contour lines, it's bathymetry. That's what I was looking for. So depth beneath sea level, but you see the continental slope there, and then the shelf out here. So here, that would be a slightly different story, because we've got this inlet here. So the baylands would flood. Those are all low-lying. There's a lot of marsh along the inside of the bay. But out here, we've got a pretty steep coastline, and that would be protected. Let's look at sea level fluctuation in the last 500,000 years to get an idea what it's looked like in the past. So here's today on the left at 0,000 years ago. And we're going back, there's 100,000, 200,000, 300,000, 400,000, 500,000 years ago. Here's modern sea level in the blue dashed line. And then what it's showing is the last glacial maximum at about 20,000 years ago. Sea level was 120 meters. 120 meters, that's 360 feet lower than it was today. And that's what got us the coastline, the beaches outside the Farallon Islands. And then it slowly rose with some variability up to a high stand at the last interglacial period. So when all the glaciers, not all of the glaciers have melted, but a lot of the continental ice had shrunk. And this high stand here, that puts sea level, let's see, these are 10, 20, 30, these are 10 meter lines. So it's about 10 meters higher than today. 10 meters is 30 feet. think globally, not just here, that's going to have a huge impact on a lot of the low-lying islands in the South Pacific, in Southeast Asia. That's going to have a big impact on low-lying, like passive margins, like the East Coast and Florida. They're really at risk. Then the glacial and interglacial period that happened before that, here's the last glacial period here, around 140, 130,000 years. And then it varied again to almost about today's sea level. And then you see like the same kind of variability going back and past. So these are natural fluctuations. And it would be much easier to predict where that curve will go in the future if we knew that nature was just following its course. Of course, we've contributed to global warming, and so we're no longer relying just on nature's signals. We've had a chemical input into nature, and that's going to cause warming and therefore less ice on land, more water in the oceans. Okay, so if we look at just how sand is transported and all kinds of sediment. I'm just saying sand because sand is what ends up coming out at the mouth of these rivers. So here we've got rivers bringing sand from the mountains. We can just think of this as like the Sierra Nevada back there. Dams, this could be like the dam that's on Hetch Hetchy that is like a submerged Yosemite Valley where we store water for San Francisco and the Bay Area, a lot of it. Some of that, so some sand gets trapped here and so starves the ocean from some of the sand that it otherwise would have to feed the beaches. But when it gets down, the fine sands and silts and clays get down to the coastline, longshore drift. So these are the waves coming in and they're coming in at an angle to the coast. So longshore drift is going to the right along with these arrows. That's a natural process, except that we're interrupting it. We're interrupting it by removing some of the sediment, by holding it behind a dam. We're interrupting it by creating harbors where you prevent sand from being deposited here. And what happens is you just get sand forming little, what's called a spit at the end of these, I don't know what to call this, a pier, a jetty. And it can fill in the harbor unless dredging happens. So they actually go in, they dig up the sediment, and then they send it somewhere else, maybe the other side of this jetty, to prevent it from filling in the harbor. A jetty like this is also going to have an effect because the longshore drift is bringing sand. And so you're going to get sand deposition here on the upward flow side of the jetty. And then you're going to get erosion on the far side. So that's going to have an effect on the beach. And so if you want to keep your beaches, and that's good for tourism, that's good for people who live there, they want beaches, right? They don't want to lose their beaches to this kind of erosion. And so we have to interfere again to try to correct the problems that are caused by things like creating harbors and damming up sediment. Now, where does all this sand go? Eventually, it makes its way to one of these submarine canyons. And if you like, the Monterey Bay has the Monterey Canyon. That's a huge submarine canyon. I've got images coming where turbidity currents can send these underwater landslides essentially down these canyons at a rapid pace, and they get deposited at the bottom. And then you would require new or different rivers providing new sand on this, if we think of that as the south, on the south side of the submarine canyon there. Okay, so this is what I've been saying. Here's the surf coming in. The waves are approaching at an angle. you get this, they're refracting and getting more parallel to the coast. But the sand is moving up and back and forth up the coastline with the wave action. But it's gradually moving in the direction of the longshore drift. All right, I think we covered that enough. I think I already showed images, unless I'm forgetting, maybe I didn't yet. I'm just remembering putting this together for you. Okay, so in the summertime, our beaches are full of sand because the waves that are coming in are gentle. Why? Why are they gentler than during the winter when we have big waves at the coast? It's the storms that are out in the ocean somewhere where we can't see, right? We can't see the storms. The satellite imagery can see the storms. So we know if there's big waves, if there are big waves approaching. But in the summertime, we don't have so many storms. And so the wave action is gentler and it moves sand from just offshore in sandbars to on the beach. And you get like a berm formed, nice flat beach behind the berm, and then a steeper beach profile on the wave side. In the wintertime, what happens to that sand? The sand, the waves erode the sand from the beach and bring it out and deposit it on one of these sandbars. So that would be out at where the water depths are greater than half the wavelength of the waves. So here's a wavelength between crest to crest, right? Or trough to trough, but crest to crest here, there's a wavelength. And so half of that distance, if you consider that water depth, that's where the waves start to feel bottom. And that's where they start to affect the bottom, the floor, the sea floor. So to form ripples, and you're moving sand around. But outside of at greater depths than that, that's where the sandbar is getting deposited. And that's where the bottom isn't affected by the wave action. Okay. So here's what the one beach might look like in the summertime, where there's plenty of sand out here. And then in the wintertime, I don't think you can see, I don't think that's beach. I think that's all water. So this is what I'm talking about, like storms and all the wave action. So that's going to take this sand offshore, bury it in one of those sandbars. Here's another one down in La Jolla. That was Santa Cruz, its beach. And then this is La Jolla. Here's a summertime beach, looks beautiful. Here's the wintertime, same beach, except now it's cobbles. Where's the sand? It's taken the fine material, it's left the cobbles behind. They're too heavy to move completely. But all the fine material, the sand, the silt, the clay, size particles are now offshore. So very different looking beaches. Yeah, and you're just seeing, you get closer to seeing what the wave cut platform looks like at that stage in the winter when the sand is removed. Okay, the name of one of these cells where we've got rivers bringing sediment in and then and sand being transported along the longshore current, along the longshore drift, and then deposited in to a submarine canyon. That's kind of the end of one of these, what are called littoral cells. So that's the term for the circulation by longshore drift of the sand. So you're getting littoral drift is this longshore drift of the sand from along bays, along the straight coastlines, and then to their demise, I suppose, in the submarine canyon. There are a lot of these along the coast. There are 25 different named littoral cells along the coastline. And so where I am, I guess I'm number 13. I'm just above this little bump north of Half Moon Bay. Littoral cell. So there must be a a submarine canyon not too far south of here. I should check that out. Monterey Canyon, of course, is the Grand Canyon of all submarine canyons. That's this one here, number 15, 16. It must be 15 because it ends in the middle of that bay, of Monterey Bay, where the canyon starts. In Southern California, I know some of you are in Southern California, so I made sure to put in some Southern California material for you guys. So I hope you appreciate. Here's the direction of the longshore transport, and here are some of these littoral cells. So Santa Barbara goes off into this Mugu Canyon. The Santa Monica comes in here along Santa Monica Beach and comes out the Redondo Canyon. Again, south of LA, the San Pedro one, and then Oceanside, out the La Jolla Canyon, and so forth. Many submarine canyons keeping this process working. Here's Monterey Canyon, Monterey Bay Canyon. So here's the bay. There's Santa Cruz. Here's the bay. So Salinas is in, well, there's Moss Landing. Moss Landing is where those big, if you drive down to Monterey along the coast, that's where those big smokestacks are. And there are harbors in there, a couple. This is, oh, I'm forgetting it. There are otters and lots of seals. Emma, what's the name of that place where we go kayaking down by Moss Beach? Shoot. You don't remember, do you? Where the otters are?
You're talking to me?
Yeah.
Oh, what did you ask me?
Where we go kayaking down Monterey.
No.
Oh, fine. Useless. If it'll come to me and I'll remind you guys, because you can rent kayaks out there. It's awesome. And Elkhorn Slough, that's what it is. Elkhorn Slough, ELK Horn. And if you get the tide's right, so that you go into Elkhorn Slough when the tide is rising, it'll help push your kayak in and you won't have to fight the tide. And you go into the slough and it's gorgeous, it's peaceful, and the otters come up next to your kayak. It's awesome. There's also a state beach out here where you can go, especially like at sunset time, at dusk. They're hanging out in that little bay that's right on the coast. And then you got to time your kayak right, so that you don't want to be trying to come out that Elkhorn Slough when the tide is rising. You want the tide to be going out. Otherwise, because the tide is funneled through the mouth of the river, which is fairly narrow, some strong currents form. And anyway, that's a fun thing to do if you haven't done that before. But that area right there is the head of the Monterey Canyon. And so that's where all the sand that is deposited along the Santa Cruz beaches and in that entire littoral cell, and then it falls down the canyon in these landslides. It is just like the Grand Canyon. Here's a profile of the Grand Canyon. At the same scale, here's Monterey Canyon. They are just as deep and almost as much volume. If you were to like measure this whole volume there, it's a huge canyon. And I showed you some more images of it, of these, the imagery showing, I guess, I don't know, do they use LiDAR, submarine radar, to get these beautiful images? It almost looks like an underwater river here, right? It's essentially how it works. At the bottom, where it flattens out, so right here, this is the slope, the continental slope, right? We've got the shelf that's flat, and then the slope is where it's like a underwater cliff where it dives down toward the deeper ocean basins. And where it flattens out is where all that material is going to be deposited, right? As soon as those turbidity currents, those underwater landslides, they reach the flat land, they slow down, and all of the material gets deposited at that point. Here's what it kind of looks like. So a submarine canyon, here's the shelf, and then here's what one of these submarine fans would look like, where you're going from that continental slope where it's steep to the flat abyssal plain, and you get the deposition. So the velocity of those currents slows down and the material gets deposited. This is kind of what it looks like underwater. So instead of being like it's a landslide in the sense that like there's heavy material at the base of it, but the fine material that would be dust if it was subaerial, but because this is submarine, that fine material, the clays, the silts, is kicked up in a plume. And so it looks like this, like a cloudy plume of clay, silt coming down. So you get deposits. I think I have an image of what one of these deposits, maybe I don't. One of these deposits, nah, sorry. You can actually see this in the rock record with coarse material at the bottom, and it gets finer as you go up. You even see ripples in it, but you can see these sequences that are the deposits that happen down here in the submarine fans, or even higher up on the slope. But anyway, so I have a short, it's a shortish video. I think it might be 5 minutes. I think it's worth watching. The Surfrider Foundation is a nonprofit that is, they want to maintain the coastline for everybody's use. They want to find some happy medium where everybody can use the coast and not deplete it of its resources. So to stop beach erosion, and as far like mitigating these structures that are built on the shoreline that have an impact, like jetties have an impact on the flow, that river of sand that happens in longshore drift. So let's check this out. Where's the sound?
Deal is, where does this come from?
Wait, let me pause it. Maybe it needs to catch up a little bit. We can come back to this if it's not gonna.
Activity affected that. Somewhere between probably 75% and 95% of the sand on California's beaches comes out of our rivers and streams. Modest amount comes out of eroding bluffs, but the bluffs have to be sandy. San Diego is a bit of an exception where the bluffs seem to be sandier. There seem to be fewer streams providing sand, so it may be even half down there.
Yeah, the lack of sand is exacerbated by dams up our rivers, jetties, and other structures like Oceanside Harbor, Bataquitos Lagoon, also seawalls retain sand.
Concrete structures that are sort of up in the watershed have impounded or inhibited that sand from coming down the rivers and out onto the beaches.
And wherever we build anything that extends out into the surf zone, into that literal transport zone, we're going to trap the sand, just like a dam on the streams. One of the things we've done on a large scale is coastal engineering structures. And California has not only some big harbors with major breakwaters, but lots of smaller marinas and harbors.
One of the issues that we've been dealing with a lot in the Surfrider Foundation is the fight against seawalls. One of the problems with seawalls is that wherever you put a seawall, it's on an eroding beach. And through a process called passive erosion, you slowly lose your beach.
When you set the back beach, whether it's a seawall or a parking lot or a railroad or a highway, and sea level continues to rise, but the beach can't migrate, basically you drown, you flood the beach.
What we're seeing is that line, the ocean trying to push that line for inland. We're trying to hold it in place, and the part that gets stuck in the middle there is the beach. So it's that sandy interface between the land and the sea. If we continue to hold that line in place, but sea levels continue to rise and beaches continue to erode, eventually we will have no beach in many places.
So we've definitely engineered the coastline, and there's a cost to that.
What we really need to do is come up with a plan that, one, makes sure that nobody builds on the edge of a bluff. And if they build on the edge of the bluff, they automatically waive their right to build a seawall in the future. And eventually what we really want to see is planned retreat.
Planned retreat is a concept whereby, since the property owners are using public beach to build their seawalls, that they pay rent for the time their seawalls are in place. And at the end of that period, the rent is used to buy their properties back and remove the seawalls.
Surfrider's policy on beach dredge and fill is that it can be used as a last resort, while we advocate for a managed retreat. So moving things back from the coast, we recognize that as a temporary measure, in some places, beach nourishment may be the right choice.
One solution is not what is going to work. It took us 50 years to get in this mess. These houses should have never been built this close to the beach. The harbor and the dams probably never should have been built if our concern was getting sand flow to the beaches. So you need to supplement with sand, but that's not the only solution. You have to recognize it's an eroding coastline and find a way to start moving back. Fixing the beaches with seawalls over the long term is going to destroy the beaches forever. You'll never be able to get enough sand to overcome that erosive force.
Sea level is rising more and more rapidly. Our beaches are getting more and more narrow. With the shoreline constantly changing and wanting to move in and out naturally due to sea level rise, due to coastal erosion, due to loss of sand, we need to have our coastal managers, the people that are making decisions on where things are built, how they're built, those decisions need to be made with a sense of adaptation, of actually being able to sort of alter the way that they plan based on what scientists see coming in the future. Once we see our beaches getting to the point where people can't come and play on the coast anymore, and all you have is, mansions with rocks and concrete in front of them and ocean, and you can no longer access the beach, I think people in our society they're gonna be upset about that. I think we're gonna have to move back from the coast, from the beach, because it's sort of, the beach is the #1 tourist destination. It's where people come to relax, people come to play. And if that's taken away from them, they're gonna be angry.
Okay. So questions about that video? So the seawalls they're talking about is all the concrete that gets poured on the cliff, the sea cliffs, to try to stop the erosion that would undercut those houses, or in the case of Pacifica, those apartment buildings that I showed you, to stop that erosion. But the problem is then you cut off a supply of sand to the beaches, and you're getting erosion everywhere there isn't one of those walls, and it's going to undercut the coast. So modifying things has a negative effect on natural systems. Okay, this is just a graphic to remind me to say, but I've already mentioned the impact of a dam at one point. So like Hetch Hetchy would be part of the problem, where sediment gets trapped behind the dam. And actually they lose a lot of the capacity to hold water in those dams if too much sediment builds up. So they would have to have release every once in a while to flush some of that sediment out, or they would have to dredge behind the dam. So that there's room enough to store water and not just a bunch of sediment. But that is starving longshore drift from the supply of sand that it would need to flow naturally. River input too. So if you mine sand. And remember I said sand and gravel are one of the top components that are mined for construction of roads and just cities. If you mine sand and gravel, you're going to reduce the input from the rivers, and that's going to reduce the amount of sand that's in the longshore drift. So that's what that's about. Okay, so the orientation of the coastline has an impact on where sand is deposited. That makes sense. This is a satellite image showing Santa Cruz. So this would be a point extending out at the north side of Monterey. This is Monterey Bay, right? The Monterey Bay, Santa Cruz, that's the pier. The sea cliffs are here. It's a rocky promontory that sticks up. And so there's erosion going on here, not sand deposition. So the sand is being eroded here and transported into the bay. And those waves, you can see the incoming waves here. There's a wave here, here, here. They're starting to refract around into the bay. And that's in part why you get deposition along A, and you're getting erosion more so along B and along here, the unmarked part. So the east-west orientation there helps to form this wide, stable beach versus a north-south orientation where there's no barrier to sand flow, and you get very narrow beaches or no beach at all. And so the whole north-south thing depends on where you are. On the west coast or on the east coast, it's going to be rotated, right? It's going to be the other direction. But both along the east coast and the west coast, the longshore current is moving south. This is Ventura Harbor. So again, the harbor, you want boats to come in and out. And these jetties and like this man-made structure here, what would I call it? A gravel bar, something like that, some kind of bar. And these jetties are to try to keep sand from filling in the harbor. But of course, the sand is still moving southward along here, and it's still going to start to pile up here, and then gradually build up around the tip of the jetty and fill in the opening to the harbor. And I'm sure they don't want that. Therefore, they have to do this dredging. And it's been ongoing since the 70s. Good God, that's a long time. So here's there's an offshore breakwater. Breakwater, that's what you would call this thing. This is a breakwater. Okay, there's a breakwater here, just out of the picture, unfortunately, at Venice Beach. And it has the effect of, do you see how wide the beach is between the breakwater and the shore? It's really wide compared to elsewhere. So this is having the effect of sand deposition. Again, that's going to take it out of this natural system that flows with longshore drift. Coronado in Southern California. This is before and after with an El Nino storm. And there was a big El Nino storm and season in between 1997 and 1998, that winter. This is what the beach looked like before. And here's I guess we'll call it a breakwater, this rocky breakwater there. And you see the sand is being deposited up against the breakwater on the north side, and there's erosion on the south side. Here's a slightly different angle, and you see, again, there's sand deposited along the breakwater, but the beach is gone. There's a lot of beach gone. It was really wide here, and now it's much narrower. I realize we can't see quite all of it, but you get the idea. And again, erosion on this side. so it says on further south that the beach was eroded all the way back to the seawall. So the beach was gone entirely. Okay, we can do this. We're going to end up going just past 12, but we can get to the end of these slides and it's going to be great. Okay, we're going to start talking about tides. I realized I kind of got to the end of my slideshow there about longshore drift, and I had forgotten to talk about tides or ocean currents, so I had to add that in. Here we go. This is about 6 minutes.
People have been observing tides for a long time, and at first, you'd look at the water come in and out, and that was your tide observation. But in time, people, made the connection with the sun and the moon and realized that maybe to understand tides and how they work, it's better to look up at things in the sky. My name's Ben Burris, and I'm a staff astronomer at the Chabot Space and Science Center. Tides are caused by the gravitational pull of the moon and the sun and the rotation of the Earth. The Earth is not a solid sphere like you'd think. It's actually kind of squishy, especially this layer of water we have on the outside of the oceans. So the gravity of the sun and the moon actually kind of squeeze or stretch the Earth and its oceans out into a couple of bulges. One under the moon, one on the other side of the Earth. And as the Earth rotates over the course of a day, you standing on the surface of the Earth move along with the Earth's surface into these bulges. And we experience that as the rising and lowering tides. But really, we, on the surface of the Earth, are moving through bulges created by the moon's gravity and the sun's gravity as well. Now, it's easy to see how on the side facing the moon or the sun, you could get this bulge of ocean. And you can imagine the gravity pulling the oceans up into a blob or a bubble. But it's not as easy to understand why there's a bulge on the other side as well. And the easiest way to describe that is the moon's gravity is stronger, of course, the closer you get to it. So on the side of the Earth close to the moon has a stronger pull. So while the oceans on the moon's side get pulled more strongly than the general Earth does, on the other side it's kind of opposite. The pull on the oceans on the far side are less than the pull on the Earth. So that far bulge actually gets created. You can think of it as the Earth being pulled out from under the oceans a little bit. And so you get 2 high tides a day because as the Earth rotates, we rotate through these 2 bulges. Both the moon and the sun play a part in tides. Each one pulls. And when the sun and the moon combine their forces, that is, when they're both acting together, we get much stronger tides than usual. Higher highs and lower lows. We call these spring tides. The name spring tide doesn't have anything to do with the season spring, but we get them about twice a month at new moon and at full moon, when the Earth, the moon, and the sun are all lined up, and the gravity of the sun and the moon are acting together. Neap tide is when the tidal effects of sun and moon are kind of canceling each other out or making each other not as extreme. And that happens around first and third quarter phases of the moon. When the sun is in one part of the sky and the moon is 90 degrees around, and they're kind of pulling in different directions. So you get lower highs and higher lows during the neap tide. Things we've learned about the tides with things like tidal gauges is that tides are actually very complex. And with instruments, we can measure those complexities and learn a lot about not just the sun and the moon, but the Earth, and the ocean floor, and how water behaves.
That's the San Francisco or Golden Gate Tide Station, the oldest continuously operating tide station in the Western Hemisphere. So it's been in continuous operation since 1854. And it's a very important facility because it feeds us state-of-the-art information using most current technology on tide levels, currents, water temperature. We also have a small weather station attached to it, and also some information on like the surface currents as well as subsurface currents. most importantly, we're getting sea level information. It has gone from having a calibrated stick in the water, being read, manually by someone every so often, and now we have state-of-the-art equipment. It's all computerized. The data that is fed into it is gathered not only from the station itself, but also from a small breakwater. And what it does is it uploads information via satellite every 6 minutes, so that information is near real time. The world's climate is changing, and it is happening at a rapidly accelerating speed. And we need to be right on top of it, because the entire Bay Area is going to change. The configuration of the bay itself, the very fact that we have a tide station that is giving us information over a period of more than 150 years is important, because we're going to see the short-term changes as well as the long-term changes, and then be able to plan our response accordingly. So this is kind of like the front line of our data. As we see sea levels changing, this is going to be a key factor, a key piece of information in determining how those changes are occurring.
Okay, that was a nice introduction to tides. The most important thing that I think they said, apart from the fact that we had an 8-inch sea level rise in the bay since 1900, which seems like a lot, but they're talking about even more than that with global warming. So the important thing, I mentioned that we're in a spring tide right now, and it's given a special name, a king tide. I've got a note down here. It's an especially high spring tide that just happens maybe a few times a year, 3 or 4 times a year, once a quarter. And that just means the high tide is even higher, the low tide is even lower than normal. And that's, again, because we either got a full moon right now or a new moon, which means that the sun is either opposite the moon. So for a full moon, we've got they're in alignment. The moon is on the opposite side of the earth from the sun, or a new moon where the moon is between the earth and the sun. In either of those two configurations, you've got this additional gravitational pull that creates a larger bulge on the hydrosphere, on the oceans, that produce that high tide. And I thought was a pretty clever description to say that, you can imagine the bulge in the hydrosphere of the earth with that gravitational pull where the two are here, where the moon is here between the sun. But how about on the far side? That doesn't make quite as much sense. And it's because of it's like pulling the earth out from under the layer of water to produce that bulge. It's kind of like that. Okay. And then he described neap tide. So the spring tide is just when there's this alignment, has nothing to do with the seasons. And then the neap tide is when you have the first quarter or the last quarter moon, where there's 90 degrees between the moon and the sun. And so we've got different alignment of the gravitational poles that give you sort of a moderate high tide and a moderate low tide. I don't expect you to do these calculations. The point here is that this is showing the distance from the moon to the earth and the distance from the sun to the earth, and doing some calculations to figure out the tide generating force. It's the mass of the body divided by the cube of the distance. And so if you work out the math, the sun has 27 million times more mass than the moon does, and it's 390 times farther away than the moon. What the result is, the sun has about 46% of the tide generating force of the moon. So the moon has a slightly greater impact on our tides than the sun does. The global tidal range, we're talking about, okay, so the deep blues are in here between This is in meters. So between 0 and 0.2 meters, so that's 20 centimeters, 40 centimeters. Here's 1 meter in the greens. So what do we have out here? We're in the light oranges or toward the red. So somewhere in between 2 and 3 meters are our the tidal range, probably closer to 2. So what does that mean? That's about 6 feet of the range between high and low tides. And it's really variable around the world, but that's what we've got here. Some places it's really extreme. Oh, I'm forgetting the name of the bay. This bay over here in Canada, is it not Nova Scotia? I'm not remembering. It has a huge tidal range. And it's got some pretty spectacular scenery to watch that come in. Oh, right, the frequency of the tides. Okay, so this is more description of that same idea where there's an alignment between the sun and the moon to give us that tidal, the bulge that gives the spring tides, especially high tides. He said in the video that most coastal areas experience 2 low tides and 2 high tides every lunar day. So that means every 24 hours, 50 minutes. That's how long it takes for the moon to rotate around the sun. The earth, moon to rotate around the earth. But it's not quite as simple as that. There are places where you get two clear high and low tides. They're called semi-diurnal. So that's the red lines around the coast. So we don't, there's semi-diurnal tides along the East Coast. Here we have what's called a mixed semi-diurnal tide. So that's a mixture between a diurnal tide, which is one cycle, one high and one low tide. And it's a mixture. So we see this more complicated pattern. But the result is we still get 2 highs and 2 lows, but there's a variability in the low tides. Like the lows aren't at the same low level of water, and the high tides aren't at the same high level of water. Here's an actual tide table, and I've stretched it here to fill the screen. But this is the curve that you're seeing. I squished it. I reduced the vertical exaggeration here so that you could see the variability. This looks like that pattern that I just showed you here. It looks like one of these mixed semi-diurnal tides. And this is for Pacifica. Since I'm here, I just looked that up. So it's this mixed semi-diurnal tide. We get 2 different high tide levels, 2 different low tide levels. But when you look it up, and you can look this up for any area, I went to NOAA, the National Oceanographic and Atmospheric Association, I think what it stands for. And it gives you these data. It shows you when the high tides are, and when the low tides are. It gives you the timing and the actual height of the tides. And it's all referenced to a mean low water level. So it's sort of an average mark. It's right here, I put a note, high and low tides are referenced to the average low water mark. So that's what the pluses and the minuses refer to. So we look, here's one example that I pulled out. A low tide, this is for the 14th of November, a low tide at 3:01 a.m. and 4:03 p.m. So almost 12 hours apart, about 13 hours apart. And one is at 0.2 feet, so 20 centimeters above average low sea level, or low tide, and at 2.89 feet, so almost 3 feet above that average low tide. Then the high tides at 9 a.m. and 10:30 p.m., again, almost 13 hours. And those are at almost 9 feet and almost 7 feet. So that's how you read it. You can, and it gives you the moon phases too, because that has an effect on the tides. You know that if a new moon or a full moon is present, you're going to have even higher highs and lower lows. So if you're interested in surfing, you need to read the tide tables. If you're interested in going out and tide pooling, and there's some fantastic tide pools out along the coast. If you've ever been to the Fitzgerald Marine Preserve, they close that area right now, even though it's like the best time to go when we're all not at work exactly as usual. It's closed because of the pandemic. I guess they don't want people gathering because a lot of people come out to look at the tide pools. But after it's all over, it's out here. It's between Pacifica and Half Moon Bay, and it's a fantastic place to go tide pooling. Okay, the differences between the spring and the neap tides. These are the ranges in the blue lines that you're seeing. Height in the mean sea level. So -2, there's the mean sea level at 0, +2, +4. And it's just showing you the correlation between new moon and full moon and getting the high tides then, and then the low tides with the first quarter and the last quarter. So these are the moderated. So they're lower high tides and higher low tides at the first quarter and the last quarter. And here it's higher high tides and lower low tides when you've got the full and the new moon. Currents. Okay, so we're going to switch to ocean currents. Any questions about tides before we move on to currents? I just want to say a few things. I see it's 10:12. I'm going to finish hopefully in 5 minutes, okay? This is showing, these are the names of the different zones within the ocean. They've named the different epipelagic, mesopelagic, bathypelagic, abyssopelagic, and hadopelagic. Okay. These are the extreme depths of the ocean where those weird fishes with the lantern fish, I can't remember its name. The one from Finding Nemo.
Anglerfish.
Anglerfish, thank you. This is showing, here's the epipelagic zone. I wanted to show you the thermocline, the fact that there's a temperature decrease. So we've got the warmest water near surface. And then it drops off rapidly in this thermocline. So this is where it just means that there's a decrease in temperature. Thermo is temperature, cline is like incline, decline. It's a decline in this case. So it decreases significantly. So 10 degrees Celsius it's kind of a lot. You got to convert in your mind to, this is probably like 70 degrees Fahrenheit and 0 C is freezing. So this is not freezing, but it's not warm either. Okay. A summary of major ocean currents. Okay, it gets more detailed than this, and I've got a more detailed view in a second. But I wanted to show you the surface currents. So this is the warm water currents and these are all surface currents. So these are warm water currents in red and cold water currents in blue. And it makes sense that there are more cold water currents occurring near the poles, right? At the in the Arctic and the Antarctic. We do have a cold water current called the California current that comes along the West Coast. So, and it ends probably somewhere close to Southern California, where you get more tropical, warmer water near Southern California and Baja, certainly. So the change happens somewhere between Southern California and Baja California, which is Mexico. What did I want to say? I guess I'll switch to the more detailed current map. It names them for you. So you can see that there's the cold California current, there's a cold Peruvian current, and then the equatorial regions, that's where we saw the warm surface currents. That makes sense. And then you get these cells, they're called gyres. So the North Atlantic gyre, where you've got warm water that is moving towards the pole, it cools off and then cycles back down the eastern side of the Atlantic and then warms up around the equator, and the cycle continues. Same thing happens in the Pacific. So, and there are cells in the northern hemisphere and cells in the southern hemisphere that rotate opposite directions. So we see clockwise rotation of these gyres in the northern hemisphere. We've got the warm current along Japan, and then it crosses over the Pacific. It's moving toward the Arctic, cools down, and then we get the California current, which is cold, warms up in the equatorial regions, and the cycle continues. Same thing happens in the southern hemisphere, except we have counterclockwise rotation of these cells, with the same effect. Warm water moving from the equatorial regions down the coastlines to the Antarctic. The water cools down and then cycles back up as a cold current towards the equatorial regions, where it warms up, and then the cycle continues. Yeah, this shows you more of the complexities. It's just some more details about how these currents work. And I just wanted to just point those out again. You can see that there's, for the most part, you get the warm equatorial currents, and those warm currents move up toward the polar regions, cool down, and we get the cold California current there. I guess that's all I wanted to say about there. Why did I bring this here? I guess it's just showing, I can't remember exactly why I wanted to show you this, except to explain more about the California current, which is to show that that warm Japan current crosses over in the northern Pacific. So this is north of Hawaii, crosses over in northern Pacific, and that's where it's accumulating and cooling off itself. It's accumulating cold water, cooling off, because it's mixing, right? But there's a current definitely that's bringing that water across the ocean, and then you get the cold California current there, and it cycles back south of Hawaii, closer to the equator. The last few things I want to bring in are what's happening to the air, and how is that affected by the sea surface temperatures. What happens is we've got a day-night cycle. During the day, you get, you know that there's oftentimes fog along the coast. If you're in California, there's fog along the coast oftentimes, because there's cold and moist ocean air coming in from the coast, from off the ocean to the land, and the land surface is warmer in general. And what happens is you get this cold, moist air that comes in along the sea breeze. It warms up when it gets to the land. It rises up, it forms clouds because it's a moist air. That warmer air cycles back out toward the ocean. It cools off again, sinks, and then that cycle continues. At nighttime, that cycle reverses, and you get a cooler breeze coming off land, and the sea surface is warmer in a relative sense. It's more stable than the land surface temperature. And that warm air, again, which is moist, comes up and cycles back onto land, and you've got these cells like this. So there are changes in the sea breezes and how that affects the coastal weather. It certainly affects this marine layer that we get. And so here's the Golden Gate, and with the coastal clouds, the coastal fog coming in. And what's happening is, this is a little blurry. You get, let's see, this is at the peak of daytime, so 105 degrees. I thought there was a time stamp on here, I don't see it. So 105 degrees on land, maybe cooler in the mountains. That's true, like the Sierra Nevada. This is like Nevada or Reno, down in the Basin and Range, where it's really hot. It's cooler up in the Sierra Nevada, pretty hot still in the Great Valley, but then the coastal regions will be like 70 degrees. trust me, I love it here during the summer. It never gets super hot along the coast because of this the moderating effect of the ocean sea surface temperatures. You get this fog that comes in, and that will cool inland areas down, certainly. And well, okay, this isn't the Sierra Nevada. These are the coastal, these are like the Santa Cruz Mountains instead. The same, it's similar effect, but just on a different scale with the Sierra Nevada. The fog will come in, it'll cool things down. And it has a moderating effect on like summertime temperatures. So that sea breeze will help lower the land temperatures during the summer. So that's nice when we get that marine layer coming in. It reduces the heat on land. Oh, that shouldn't be here. Wait a minute. Where am I going? Sea surface temp. I had the wrong slide in here. Okay. This should have been back with the tidal ranges. So that looks very much like the map we've already looked at, where we saw, yeah, the different, where tides were very low, like just 20 centimeters, 40 centimeters versus a meter or 2 meters like we have here. So we're in like yellow. It's 120 centimeters. So that's, it's not quite 2 meters, but 1.5 meters, something like that. Somewhere in there is what we've got along our coast. Okay, last couple of slides. Oh, it's almost 20 after, but we'll do this and then we'll be done with coastlines. Sea surface temperatures. They're warm along the equator, no surprise. They're more moderate at the temperate latitudes like we have here in California, and then coldest along the Antarctic and the Arctic. That makes sense, right? That has an effect on the deeper water circulation too. I've been talking about sea surface currents. Well, there are deep ocean currents that are colder. That's where the cold water goes because it's denser than the warmer sea surface currents. So where do I start? I'll start here. So so in this case, we've got warmish water in the red colors, cold water in blue, and then where you see it in yellow, that's kind of a transition zone. Okay, let's start here where we've got a warm surface current coming up along the East Coast. Okay, so that's that warm East Coast part of that gyre, the North Atlantic gyre that we're talking about. That warm surface water comes over and it's moving toward the poles, it's moving toward the Arctic, and the heat gets released to the atmosphere and the water is cooling down. So the water cools down and it sinks. So it sinks to deeper levels, and that deep cold water cycles back down the west side of the Atlantic toward the Antarctic. And that's how we get mixing in the ocean too. There's transfer of the ocean water between the deep ocean water and the surface in this conveyor belt that we're talking about. This is thermohaline circulation. So thermo is temperature, haline refers to the salinity of the water, because the saltier the water, the denser it's going to be. Okay, so we've got cold, more saline water that is denser and sinks. It goes down to the Antarctic. You see a deep current that's cold and saline. This cold water, it splits into two. So there's a deep ocean current that goes into the Pacific, and there's one that rises up, moves to the north in the Indian Ocean. So that one warms up. There must be some ripping currents between Africa and Madagascar. It warms up and cycles through the Indian Ocean. And then this arm of that current comes into the Pacific, warms up in the Northern Pacific. And it's moving from the deeper parts of the ocean towards the surface and cycles around, warms up in the equatorial regions. And then both the Indian Ocean and the Pacific Ocean currents merge again And some of that water comes back into this Atlantic cycle, and some of it joins this southern ocean cycle down here that moves along. Kind of, there's a band of this warm surface water that sort of moves along between Antarctica and the southern tips of South America and Africa. Are there any questions about tides, about ocean currents? And this is the most superficial treatment of these ocean currents. You know, if you're interested in ocean circulation, maybe it's marine geology or oceanography that you're interested in. Oceanography, by the way, is not the study, it's not marine biology. It's not the study of whales and fishes and stuff. Oceanography deals with these ocean currents and tides and waves. And there are physical properties and there are chemical properties. So you can go either way. If you're interested in that, we do teach oceanography classes on campus too. But that's all I'm going to say here about the ocean, the seawater anyway. We'll talk more about water on land later. That's all I've got for you guys today. I'll stick around for a while to answer questions. I'm going to be here 12 to 2 tomorrow to answer questions about labs or questions you want to ask me before you take the exam. So bring those with you and I'm happy to take those. Otherwise, I'll see you on Tuesday. And have a nice weekend and good luck on the exam.
Thank you, Mary.
Thanks.
Thank you.
Bye. I see that there might be chat questions. I can answer those if, oh, maybe they're just comments. Actually, I started out sea lions where a teen tried to commit suicide by jumping into the Bay Bridge and the sea lion brought him to shore. No way. That's cool. Oh, I won't see them on Tuesday. They're gone. They're on Thanksgiving break now.